Okay, good. What about the y direction then? What about the y direction? So how could I write this in the y direction? So let's move in the positive y direction first of all. Not quite, you're almost there. So I'll stick with this one first, the x squared, okay? So the y equals x squared, okay? If I'm moving it up by a, what would be happening?
Multiplied by a. Oh, plus a,
Yeah, what would be happening? So what's the transformation? Could you give it to me in a vector?
0a.
Yeah, perfect, 0a. Okay? So basically all that's happening here is I'm moving it upwards in the positive direction by a. Okay? So that y equals x squared graph gets pushed up by a. Okay? If I want to do this in function notation, well here my function is x squared. So I'm just going to replace that function with f of x. Okay? So this is generally, I did it with an example first of all so you could see, but this is how I'd write it generally. For example, if I did y equals x cubed plus 4, okay, what would be happening here? So the cubic graph looks like this. Cubic graph looks like this. Okay. What would my new graph look like?
Multiplied by 4.
Absolutely right. It's gone up by 4 like that. Is it okay? Yeah. Okay, and I'll just very quickly, just for completeness, also do the negative one as well. Okay, f of x minus a, that just basically means move 0 and a down. So in other words, my graph would look something like this. Is that clear? Yeah. So you notice that's the positive direction, that's the negative direction. Positive direction, negative direction. But you notice now with the y direction translations, it's exactly what you think it should be. You know, if I write x squared plus 4, you think, oh right, that's upwards by 4. So that's what you think it should be. Okay. Whereas this one gets a bit wrong. Okay. X minus 3 all squared means move to the right by 3, not to the left. Is that okay? Okay, let's have a look at stretches quickly then. So stretches we kind of looked at here. I'll kind of just give them to you. So effectively, if I want to move it in the x direction, if I do f of 1 over a of x, so I'm taking x, whatever that might be, x squared for example, okay, applying my function to it, but before I apply my function to it, I'm going to divide that value by a. I'm going to divide that x value by a. So for example, I might have x over a all squared. You know, so I'm dividing the value of x by a before I do my function. Okay. So what's happening here? Anybody think? If I divide the value of x before I take my function, what's the stretch which is happening? It's in the x direction, but by how much? So the scale factor here is the opposite of what you think it should be, and Batakar, you kind of picked up on this, okay? So for example, if I had a half of x all squared, you think, okay, in the x direction by a scale factor of a half, because you see the half there. But it's not. It's a scale factor of 2, and you saw that on this graph here. You saw that on this graph here, okay? When you had this thing going on, when you had this thing, okay? You thought it should be half in the x direction, but it wasn't. It was 2 in the x direction. Do you see that? Yeah? So in other words, the graph basically becomes a little bit flatter. And it becomes a little bit flatter by a. Okay, so if it's 1 over a of f of 1 over ax, it should be a scale factor of a. I'll just very quickly, because we're running out of time a little bit, do the other one, which would be ax. Okay, that would be a stretch in the x direction by a scale factor of 1 over a. So in other words, it's a little bit squashed inwards. Okay, so that's happening in the x direction. Now you see this is if it's happening in the x direction, can you see a common theme here? If it's happening in the x direction, it's the opposite of what you think it should be. So you're happy with this one, you think it should be a to the left, it's not, it's a to the right. You're happy with this one, you think it should be a scale factor of 1 over a in the x direction, it's not, it's a scale factor of a. And likewise, if it's a in the x direction, it's a scale factor of 1 over a. Okay? So it's the opposite of what you think it should be. Basically, if it's applied to the x, so you see here this is being applied to the x, this is being applied to the x, it's next to the x in other words, it's the opposite of what you think it should be. Okay? Now if I stick with it, if I do it outside the brackets, so for example if I do a f of x, you see I apply my function first, then I multiply it by whatever it is, 2, 3, 4, a, whatever it is, okay? Would you be happy this is a stretch in the y direction by a scale factor of a? Okay, so that's exactly what you think it should be. So in other words, somebody's come along and basically pulled the graph upwards, okay, in that direction. And likewise, if I do 1 over a, f of x, so I do my function first, then I divide it by a, that's a scale factor, that's a stretch in the y direction by a scale factor of 1 over a. So in other words, somebody come along and just made it a little bit thinner, I guess. Yeah. Okay. And just very quickly, and then we'll finish off, let's do the reflection. So if I do, for example, negative f of x, so I do my function first, then make it negative, that is a reflection in the x-axis. Okay, so I get something that looks like this. Okay. So it's basically just flipped upside down in the x-axis. If I do f of negative x, that's going to be a reflection in the y-axis. Now, of course, in this case, it's not going to change because it's a symmetric graph around the y-axis, but you still get that reflection which has happened. Okay. So those are basically all the transformations that I could possibly ask. Okay. So let me